Hey everyone, so we're going to review this warm-up that I gave today, and this is a question that was repeated on your homework assignment on the very bottom. I think it was like the last 3 problems at the very bottom of your worksheet. So, and this particular question is going to definitely appear on your test, so definitely want to make sure that you guys are totally smooth on this, all right? So make sure you have a calculator and let's check this out for you, okay? So it says, under the same conditions of temperature and pressure, how many times faster will hydrogen infuse compared to carbon dioxide? So the first thing that we need to establish is something that was taught to you a while back. Which gas will effuse faster? A lighter, smaller gas particle or a heavy gas particle at the same temperature? Which one moves faster? So here's hydrogen gas. And what was the other gas? Carbon dioxide? Versus carbon dioxide. Which one will move faster under the same temperature pressure conditions? Hydrogen gas. And so that's something that we established a while ago in one of those vodcasts. I think we did the crash course chemistry, and then I had my own vodcast right after that that also kind of said the same thing. So, and it's dependent upon their molar mass. So with hydrogen, if you have a periodic table, hydrogen is 1.0, but we've got 2 of them. So this guy's molar mass is 2.0 grams per mole. Now, carbon dioxide is obviously significantly heavier. Carbon has a molar mass of 12, oxygen is 16 each, and if you add that up, I'm pretty sure you're going to get 44.0 grams per mole. So right off the bat, we have established that hydrogen is definitely going to be faster, okay, because its molar mass is smaller. These small gas particles, in order to maintain the same temperature and pressure conditions, they will have to move a little faster to maintain the same amount of energy. So if you think about it like a car crash, all right, you got this small little car, and don't make fun of my beautiful, awesome car drawing, okay? This is a fabulous car. Versus a giant pickup truck. All right, big old truck here. It's got a big, there we go. You guys like my trucks and my cars? So let's pretend like they have a head-on collision, all right? And when they have a head-on collision, I want both of the vehicles to completely stop. In other words, in order for them, after the collision, after the moment of impact, in order for them to absolutely completely stop and not move in either direction, they both have to have the same amount of energy, kinetic energy. In order for these two to have the same amount of kinetic energy, who has to be moving faster? The small little dude. So in order for this guy to have the same amount of impact so that when they crash they both completely stop, the little guy is going to have to move a little faster. Now let's just pretend, let's change the situation. Let's pretend this little car is going like, say, 20 miles per hour. And let's pretend like this guy is also going at 20 miles per hour. Now I'm going to pretend that this big old truck weighs like, say, 1 ton. A 1-ton pickup truck. Let's pretend the little car is like, I don't know, maybe 0.5 tons. And that's being pretty generous. They're actually not that heavy. But anyway, let's just pretend, okay? If they were moving the same speed and the little car weighs half as much, who will have the hardest impact? Who will have the most energy going into that crash? The giant pickup truck, right? They're both going the same speed, but since the giant pickup truck weighs so much more, he's going to have more momentum. That's what that is. When you take the mass and you times it by speed, that's momentum. So the big old truck has way more momentum. So up here, when we're looking at these two gases, if they have the same amount of energy, right? Energy for us means temperature, their relative temperature reading. In order for them to have the same amount of temperature or energy, that small guy, the hydrogen, has to move a little faster in order to have the same amount of impact. Okay, so that was kind of a review there. So we've already established that hydrogen is going to be faster. And so when we try to figure out and compare their rate of effusion, all you have to really think about is what it means when the value of R is greater than 1, than the number 1. And this makes sense to you guys, hopefully, if I say it this way. Let's put you guys out on the track. And if I say, all right, student A is 2 times faster than student B, You hear the value? 2 times faster. The value there is 2. The number 2 is greater than 1, which means that student A is faster, right? What if I switch gears now and say that student A is 0.5 times as fast as student B? Does that mean that student A is actually faster or slower? Slower. So as long as the value of R is greater than 1, that means that something is faster than the other object. But if we take R and we make the value less than 1, that actually means that something is being slow or slower. Okay. So as long as we've established that fact, you guys pretty much, you've been suffering through with this crazy gas law formula. You guys remember this? Rate A over rate B is equal to molar mass of B square root over square root molar mass A. You guys have been suffering through that formula, and you look at it and it's just like, oh, that doesn't make any sense. And I'm like, I feel you. I'm so sorry. And so I showed you guys how to rearrange that formula a little bit. And so I definitely want to review that one more time. So if we took rate A and you square it and you multiply it by the molar mass of A, that would be equal to rate B, make sure you square it, times the molar mass of B. And that's just rearranging that formula. You guys can look at the math, but that's basically rearranging this formula. It's the same thing, just rearranged. All right, but let's go to this question. We already know that hydrogen gas is going to be faster because it's the lower molar mass. What we're going to do is we're going to create an R value that is greater than 1 because we know that hydrogen is already going to be faster. When we do this whole rate thing, over on the left, this is like a ratio between element A, element B, whatever, molecule A, molecule B. And this is how we solve for rate. We use their molar masses to figure out the ratio between the rate. If we're looking for this value on the left to be greater than 1, whose molar mass do you think we should put on the top, 44 or 2? I'm going to repeat that question one more time and make sure you got it, okay? If we want this guy's value to be greater than 1, because we already know that hydrogen's faster, whose molar mass should go on the top? Should we put 2.0 here? Or should we put 44.0 here? You want the larger value on the top, right? So if we're looking for our R, I'm just changing this. This is like a ratio between the two values, the two rates. If we want R to be greater than 1, I'm always going to put the larger molar mass on the top. So I'm going to put this 44.0 on the top, and I'm going to put the 2.0 on the bottom. And when you solve, you're going to get a value that's going to tell you how much faster hydrogen is. Because we already know that hydrogen is faster. Go back to the question. It actually already says, under the same conditions of temperature and pressure, how many times faster will hydrogen diffuse compared to carbon dioxide? So we've already established that hydrogen is faster. Let's just get that rate comparison, that ratio. That's what this is. It's a ratio between the two values. All right, so calculator time. Make sure you know how to use your square root button, and when you get your answer, you better make sure that you're comparing with this, okay, with what we're about to show you. I like to use parentheses a lot, so feel free to use on the numerator some parentheses for that square root thing. All right, you guys, did you get 4.6904, etc., etc.? You guys good? Nice. You see how the value is larger than 1. So the way that this would work is you would just say that hydrogen is this many times faster than carbon dioxide. And if you're worried about sig figs, these rate values are meant to be kind of dependent upon how many sig figs you use in your molar mass. So knowing that, like, we can get more digits on here if we use the periodic table and get all of the numbers on the molar mass, right? But we didn't do that. So for us, I would be happy if you look up here, if you just go with like 2 sig figs. So if you want to reduce this down to, say, 4.7 times faster than CO2, and there's your answer. All right, we do have a question. What's up? The question was, do I want you to use the full molar mass? Not until you come into AP Chemistry. Don't worry about it right now. All right, I hope that helps. We're going to switch gears now, and we're going to look at your homework. So go ahead and pull that out, and make sure you have a calculator to go with. All right, from my students, they have told me that the bottom half of this worksheet seems to be where we're getting most caught up on snagging. So what I'm going to do is I'm just going to go for it. Guys, which one do you guys want to see? 21? All right. So we'll start with 21, and then if we have enough time, we'll slip over and go to the study guide too, okay? So stay tuned. Here we go. So it says, calculate the ratio of the velocity of helium atoms to fluorine molecules at the same temperature. All right, so same as the warm-up, same method. So we're going to look at helium. Helium is a noble gas. Do you guys need to put a little subscript of 2? No, because he is a noble gas. He can stand alone. So the molar mass of helium is 4.0 grams per mole. Now fluorine, on the other hand, fluorine is a gas. He's a nonmetal, but he's not a noble gas. So we're going to definitely need to put a subscript of 2. Fluorine on the periodic table has a molar mass of 19, and you need to double that. So this is going to be 38.0 grams per mole. All right, guys, who's going to be faster? Helium. Good. So we've already established who's faster. Now we're going to do that whole thing about comparing their velocity, comparing their rates. Okay, remember, rate could be velocity or the actual amount of gas that's passing over a certain amount of time. So it could be like, for rate, it could be meters per second or milliliters per hour. All right, so it could be a quantity of distance or a quantity of volume over time. All right, so anyway, so we know that helium is going to be faster. If I'm going to set up this thing rate and I want it to be larger than 1, I'm going to put the larger mass on the top. So I'm going to put the 38.0 on the top, and I'm going to put the 4.0 on the bottom. All right, let's see if we do it right here. Okay, my rate is equal to 3.082, and it keeps going. I'm going to simplify that down into 2 sig figs, so I'm going to call it 3.1. So what this means, we already know that helium is faster, but now we can say it this way. We can say helium is 3.1 times faster than fluorine gas. All right, and that answers the question. Done. Okay, coming back. What else would you guys like to look at? Some partial pressures, hopefully. 16? You got it. Air is a mixture of gases by percentage, and so we're given all the percentages. If atmospheric pressure is 760 millimeters of mercury, what is the partial pressure for each? All right, so I'm going to review one of the formulas I gave you guys a while back. So the partial pressure of any gas would be equal to this, mole fraction thing, mole fraction, times the total pressure of the system. So here, this is the formula. But really, what a mole fraction is it's kind of like a number that will always be less than 1, right? And it's dependent, what you do is you put the number of moles that you're looking for over the total number of moles in the system, and so it becomes a fraction. Well, we don't have fractions. We were given these percentages. But guys, remember, these percentages can be turned into fractions. All you have to do with these percents is divide by 100 to change them into like a decimal, and they will be less than 1 when you do that. So if I were solving for the partial pressure of, let's say, nitrogen gas, what I do is I take this percentage, 78, and change it into a decimal, 0.78. And then multiply that by the total pressure of the system, which was given in the problem right here, 760 mmHg. And so we'll do that for each of the gases. So the partial pressure of our oxygen, just change that percentage to a decimal, so 0.21 times 760 mmHg. And finally, your argon. Partial pressure argon. This was 1%. Make sure you're very careful about your math there. mmHg. All right, so this is how you solve for each of the partial pressures, and when you do that, when you get those answers, make sure they kind of add up close to 760 millimeters of mercury. I want you to realize that these percentages are kind of, rounded. There's no decimal points on those percentages. So you're probably, when you add up all of their partial pressures because of all the rounding that we did, you're probably not going to get 760, but you'll get kind of close. All right, so there you go. That's that. That's how you do that. Okay, coming back. Looking around, yeah? Sure. The question was, when it asks for ratio, are they just asking for how much faster? Yes, yeah, pretty much. So, and notice in both of these questions down here on the bottom right here, 20, 21, and 22. Oh, and actually 19 as well. It's always the little guy that'll be faster. And then when they ask you about rate, or if they ask you about speed or effusion or velocity, any of those words, you're always going to pick the faster one, put the larger mass on the top, the smaller mass on the bottom. All right, another question here. The question was, when they ask you for a ratio, what kind of units would you have? There's no units. For me, like when I speak to someone about how fast they are, like go back to that whole analogy of the runners on the track, I wouldn't say, oh, he is 5.0 meters per second faster than someone else, although I could say that, right? I could do that. But when we're comparing ratios and velocities, and we just say, hey, he's twice as fast, do I need to say he's 2.0? Yeah, we're not going to go into those kind of details. So good question. All right, any others? Yeah, right here. All right, the question was, can I do 18? We kind of have to have the answers to 17 in order to do that.
Oh yeah, I got.
All right, hey guys, all you're going to do is whatever your answer was to number 17, whatever that is, you see this percentage? What do you think you're going to do? Come back. What are you going to do? Because you've got this, and they're asking you for how much of that pressure is actually oxygen, right? You have the pressure of the gas in the front, of the air mixture, right? 22% of that pressure is oxygen. So all you're going to do is multiply whatever your answer was by the decimal 0.22. Right? Did that kind of help you? All right. All right, I think I've given you guys enough information about this worksheet. I hope you're really comfortable now and you're feeling much more secure. So what we'll do is we'll actually switch gears now and look at the study guide. All right, so now we're looking at the study guide, and I did want to kind of draw your attention to the numbering over on the far left-hand side. These questions actually came straight from your actual textbook. That's why the numbers are like weird. It goes like from 1 to 3 to 6 and 7, because they coordinate to specific pages in the textbook. So if you ever want to have a textbook to take home or anything like that, all you have to do is just ask and I'll check it out to you. All right, a lot of people are concerned about this particular question right here from page 405. Number 3. All right, what is the rate of effusion for a gas that has a molar mass twice that of a gas that effuses at a rate of 3.6 moles per minute? Cool. All right, so I don't really know what these gases are. That's kind of part of the fun. So I'm going to go molar mass A versus molar mass B, okay? Now, it says that the molar mass is twice, like 2 times. So if I just arbitrarily assign a molar mass of 1 to A, what do you think B is going to be since it's twice that? A 2. All right, so let's see, it says, what is the rate of effusion of a gas that has a molar mass twice that of a gas that effuses? So careful, the way it's supposed to be read is you've got a gas that is effusing at one particular rate, and then you have another gas that's effusing at this specific rate. So if the gas is heavier, do you see how it's heavier? Twice that. Mass is twice that. Where should I put this rate? Should I put this rate with A or should I put this rate with B? I want to make sure you guys understand that. So the rate that was given is the rate of the gas that is lighter. So what is the rate of effusion of a gas that has a molar mass twice. So we don't know what this guy's rate is. Okay, it says, what is the rate of effusion of a gas that has a molar mass that is twice? So the guy's molar mass is twice as big. We don't have his rate. We have this guy's rate. And it's 3.6 mole per minute. All right, so it's your choice on which form of that crazy gas law you guys want to use. I really like this one. I don't know, it just makes way more sense. I'm going to do this, watch. So I'm going to go the rate of A squared times the molar mass of A is equal to the rate of B, squared, ignore that, times the molar mass of B. So I like this one. It just looks prettier. So, all right. So the rate of A squared, A, okay, we'll call this A and we'll call that B. All right. Over here, we're going to plug in this 3.6, and that would be moles per minute. But make sure you do square that value, times the molar mass of A, which we arbitrarily gave the value of 1. The rate of B, we don't know. We're trying to solve for that, but do make sure that you don't forget that that needs to be squared. And the molar mass of B, we just arbitrarily said is 2, because it's twice as big. All right, let's go through some simplification, shall we? I'm going to take that 3.6 and I'm going to square that like right now. Get that done and times it by 1. So this whole left side right here will reduce down to 12.96. And we're going to say that that is equal to RB. Make sure you don't forget that that's going to. All right, so obviously I'm going to get rid of that 2 that's attached to that rate squared. So I'm going to take my value 12.96 and I'm just going to divide by 2. All right, when I do divide by 2, I get 6.48, and that's equal to my r squared, so I got to make sure at this point, guys, how do we get r? Just r. Yeah, we're going to do a square root right here. All right, so I've got that value. I'm going to make sure I do a square root of that value on my calculator. Here we go. So I've got 2.545, etc. is equal to r. So probably reducing a little bit. I don't know. What do you guys think? Should we go with 2 sig figs? Probably 2 would be best. So 1, 2. So we should say 2.5, and the unit for the rate will be the same as the initial unit up here that was given. So this is in moles per minute. All right, so mole per minute. Final answer. And I've already checked the answer in the book, and that is the answer. So whoop, whoop, did it right. All right, so I got a request from my students to do this problem right here. Number 30 on page 455. All right. All right, so it says an ideal gas has a volume of 30 liters. If the number of moles of gas and temperature are doubled while the pressure remains constant, what is the new volume? Okay. So for this one, guys, I would suggest that you kind of think through this one. If your initial volume is 30 liters, it says if the number of moles in the gas and the temperature are doubled, hold on, so the number of moles, let's just pretend like it starts at 1, and the temperature, let's also just, arbitrarily give it a value of 1. But then it says that both of these are doubled, so I'm going to go to N2, and I'm going to be like, okay, the number of moles doubled, my temperature also doubled. What is the new volume? So I'm going to go like V2 is like question mark. All right, you see how I just arbitrarily gave values of like 1 versus 2 because it says that stuff doubled? All right. So think back to your gas laws. You have 2 different values going on here. So if you think about like P1 V1 over T1 N1 is equal to P2 V2 T2 and N2. So if I were you, I would memorize that temperature and moles always gets tucked underneath on the combined gas law. Temperature and moles are always tucked on the bottom. They're divided. But anyway, so notice in here they didn't talk at all about pressure at all. So what that means for us is that we're going to omit that from the problem. So just anything that is not provided, you take out. All right, anything not provided, you just take out. All right, so let's start plugging in some of this cool stuff and see what you guys think, okay? So the initial volume was 30 liters. The initial temperature, let's just give it a value of 1, moles, 1. And then we have this second volume over here. But now over here, this is like a 2, and this is a 2. Alright, you guys, in order to make the two sides equal, what do you think that numerator's value needs to be? Some of you guys can actually eyeball this, and some of you guys are probably going to need to actually solve, which is fine, I don't care. Over on the left, if you reduce and simplify, this is going to be 30 is equal to, now if you just go x over 2 times 2 is what, 4? How can you make this equal to 30? Yeah, take that 30, the value 30, and multiply it by 4. And what do you get? 120. Yeah, so the volume's going to have to change to 120. That's it. That's the correct answer. Or you can say that the volume's going to have to quadruple. That could also be like the answer if you want. Hey guys, something that some of my students brought up is question number 13 on page 450 says, if the temperature in the gas cylinder on the right, you see that? You're going to need to actually go to the textbook and look at that picture. So don't forget that in this unit I did put a PDF of the chapter towards the top. So come back up here, it says chapter 13 from the textbook for reference only. So anyway, find that question, find that page number, and you should be able to answer that question just fine, okay? Hope that helps.